Hello, students. We're going to be working on our second day of notes with logarithmic functions and differentiation. We'll be looking at some different differentiation strategies and using those with logarithms. So the first one is implicit differentiation. And remember that this is useful when you have an x and a y in an equation and it's not easily solved for the y. So we have 4xy plus the natural log of x squared y equals 7. I do think that we should start with a rewrite on this because we can take care of this product by rewriting this as a sum. So we'll have our 4xy, we'll have to leave that. But we can rewrite this as the natural log of x squared plus the natural log of y equaling 7. And we can actually do one more step, bringing the 2 in front. So 4xy plus 2 times the natural log of x plus the natural log of y equaling 7. And then we'll do the derivative of each side. And so it's been a while, I realize, since we've done implicit differentiation. So the notation that we used in the first semester was derivative with respect to x, and then we wrote what we were going to do the derivative of. So the 4xy plus 2 natural log of x plus natural log of y equaling 7. Remember that you do this to both sides of the equal sign. So now one thing we'll have to notice is we do have a product here. So we'll need to do the product rule. So remember that it would be first times the derivative of the second. Now the second is a y, so that would be a 1, but because it's a y, we would have dy dx. All right, plus, and then second, which would be your y, times the derivative of the first, which would be the 4. So there's the derivative of the 4xy. Then the derivative of 2 times the natural log of x, that would be 2 times 1 over x. And then the natural log of y, we would have 1 over y. Because it's a y, we'll have to have dy dx. And then the derivative of the 7, which is 0. So then hopefully you can recollect that your next step is to solve for dy dx. So now that you've taken the derivative, then we want to get the dy dx by itself. So the two terms that have dy dx in them we'll leave on the left-hand side of the equal sign. So 4x dy dx plus 1 over y dy dx equals, and then I'm going to subtract this term over, so negative 4y and minus 2 over x. Substitute or subtracting that from both sides of the equal sign. Now I can factor out the common factor of dy dx. And that would give me 4x plus 1 over y equals negative 4y minus, or excuse me, there, negative 4y minus 2 over x. And before I do my dividing or multiplying by a reciprocal, I really need one fraction here and one fraction here. So I'm going to multiply. I'm going to put this over 1, multiply by y over y. And so I'll have the derivative with respect to x, derivative of y with respect to x, of 4xy plus 1 all over y equals, and then likewise I'm going to put this over 1, multiply top and bottom by x, and I'll have negative 4xy minus 2 all over x. So now to get dy dx by itself, I can multiply by this reciprocal. So I'll have dy dx equaling, and then the reciprocal multiplied on both sides would give me y times negative 4xy minus 2 over, and then for my denominator, I'll have x times, and then the 4xy plus 1. And you can leave that as your final answer for a dy dx, because if you did have to go any further, we would have to give you an ordered pair. So for example, if you needed to find the slope of a tangent line, you would need an ordered pair because you would need both an x and a y. So this is a good form to leave your final answer in. And this is implicit differentiation when you have a logarithm. Now, I'm going to go on to the next strategy. Now, this one is not a strategy that we have used before, but it's called logarithmic differentiation. It's, as I've got in the paragraph there, it's more convenient sometimes to use logarithms when you have roots, products, or quotients, because the logarithm will allow you to separate them into individual terms. So notice that in our example, we do not have a logarithm, but we're actually going to introduce a logarithm into the problem so that we can do the derivative of the logarithm as individual terms, rather than, as you see from the problem that I have, if I did the derivative right now, I would have a chain rule, and I would either have to multiply all this out or do some kind of a product rule. So you'll take the log of each side. So we're going to introduce a logarithm, and this is actually then considered to be a rewrite. So I'm going to do the natural log of y equals, and then the natural log of, now I am going to go ahead and do one simplification. Rather than having the square root, I'm going to write all of that to the 1/2 power. So x squared times x plus 1 times x plus 2, and then all of that to the 1/2 power. So that would be the first step of the rewrite process. And then I'm going to continue to rewrite. So the natural log of y. Remember that products can be rewritten as the logarithm of individual terms in addition. I'm also going to bring this 1/2 in front. So I could have 1/2 and then do the natural log of x squared plus the natural log of x plus 1 plus the natural log of x plus 2. All right, and I can do one other rewrite. I can bring the 2 in front of the first natural log. So 1/2, and then 2 natural log of x plus natural log x plus 1 plus natural log x plus 2. And let me get rid of this update message. All right. So we'll have that as the last step of our rewrite. And now we're going to do the derivative. So we'll differentiate. And, oops. I think I got a little crazy there. Sorry about that. So we'll differentiate. And so to do that, we'll have 1 over y. Remember, we have to do this to both sides. Because this is a y, we'll have dy dx equals 1/2 times. All right, now we'll have 2 times 1 over x times the derivative of x, which is 1, plus 1 over x plus 1 times the derivative of x plus 1, which is also 1, and plus 1 over x plus 2 times the derivative of the x plus 2, which is a 1. And then we can simplify by getting common denominators. I'll go through that here in just a second. I'm going to leave this as 1 over y dy dx equals, you can distribute the 1/2, but I think I'd rather just leave it as it is. So 2 times 1 over x times 1, that'll be 2 over x plus, and then we'll have 1 over x plus 1 plus 1 over x plus 2. And I did leave myself some space to get a common denominator. So your common denominator would be x times x plus 1 times x plus 2. So this first fraction would have to be multiplied by x plus 1 and x plus 2 in the numerator and denominator. This fraction would have to be multiplied by x and x plus 2. And your third one is going to have to be multiplied also by x and x plus 1. So this would give us 1 over y dy dx equals 1/2. And then, unfortunately, you're going to have to multiply all this out. So x plus 1 times x plus 2 times another 2 is going to give you 2 times, and then you'll have x squared. So that's going to be 2x squared. And then you'll have 2x and 1x. That's 3x. Taking that times 2 would be plus 6x. And then 1 times 2 is 2 times this other 2. That would be plus 4. All right, now that should be the hardest multiplication that we'll have to do. Then we're taking 1x, so x times x plus 2. So that would be plus x squared plus 2x. And then we're taking 1x times x plus 1. So plus x squared plus x. And then our denominator which is the common denominator of x, and x plus 1, and x plus 2 multiplied together. So then we can combine like terms, and we're nearly there. 1 over y dy dx equals 1/2. And then we have like terms, 2x squared and x squared and x squared. It's going to make 4x squared. We have 6x added to x, added to another 2x. That's going to be plus 9x. And then our constant 4. Again, your common denominator of x times x plus 1 times x plus 2. You don't need to multiply out the denominator. And so this is very close to the final answer, but your final answer should be solved for dy dx. So we often forget that at the beginning we had 1 over y. So you'll need to multiply both sides by y over 1, giving you as a final answer dy dx equals, the 2 could actually go to the denominator now. So 4x squared plus 9x plus 4, and this is a 4 here at the beginning, over 2x times x plus 1 times x plus 2. And then in your numerator, since we multiplied by the reciprocal of 1 over y, we would have a y in our numerator. Now, you'll see that sometimes you'll find answers where the original problem is substituted in for the y. So sometimes they'll go back and put in this, for example, this square root, substituting that in place of the y, and then doing some other simplifying. I don't think that that's going to be necessary for us, and I am not going to require it, but it is a simplification strategy that you can follow. So once again, this is called logarithmic differentiation. It's where you introduce a logarithm into the problem. It's useful if you have roots and products, especially if they're difficult to get rid of. The differentiation process is easier. Simplifying it may not be as easy, but it's just a strategy to follow. And then on the bottom of your page, you have one other application, and that is just showing that you have the solution of a differential equation. And that's nothing more than just doing the derivative and the second derivative and making substitutions. So if your original problem is y equals 2 times the natural log of x plus 3, then we can do y prime, which would be 2 times 1 over x plus 3, and, just 2 times 1 over x, it would not be plus 3. And you could rewrite that as 2 over x, or since you do have to do the second derivative, you could go ahead and write that as 2x to the negative 1 power. You do need to do the second derivative because your equation has a second derivative in it. So y double prime would be, using this form, negative 2x to the negative 2 power. Now, it might be useful to have it as the fraction negative 2 over x to the second. So now you're going to the differential equation. We're going to substitute in. So we have x, y double prime plus y prime equaling 0. We just need to show that that is true. So x times the double prime, which is negative 2 over x squared, plus, and then the y prime, which is 2 over x to the first. And we just need to verify that this equals 0. So we want to verify that we get 0. Well, the x's here would cancel, leaving us with negative 2 over x, because again, the x's would cancel, leaving negative 2 over x plus 2 over x, and indeed we do get 0. So 0 equals 0, and we do have a solution. So y equals 2 natural log of x plus 3, didn't write that right, is a solution. So 2 natural log of x plus 3 is a solution. Okay, and that's what you'll be asked to do if you have to show that something is a solution of a differential equation.